Welcome back to the Blackboard. We are back with our first example of this lecture. We are going to do a little bit, as always, a little bit easy things before we get into the more in-depth and quote-unquote harder, which technically is just more work. So in this example, we are asked to find the eigenvalues, and for each eigenvalue, we have to find the dimension of the corresponding eigenspace. And so the first part is something that we've been doing over and over again. It's the second part that's kind of new to us, but I promise you this is really simple. And a matter of fact, it's a lot less work than you think. So let's get started. And so for the first part, we are given a 2x2 matrix. Again, this is all symmetrical matrices. So this matrix is a 2x2 symmetrical matrix, and as always, we find our characteristic equation. So our characteristic equation will be the determinant. So this would be 3 minus lambda quantity squared minus 1 is equal to 0. And when we expand it, we get lambda squared plus 9 minus 6 lambda minus 1, or lambda squared minus 6 lambda plus 8. And again, it's equal to 0, but we can factor it to being lambda minus 4 times lambda minus 2. And so our eigenvalues will be lambda is equal to 2 and 4. And so to find our eigenspace, well, that is just the dimension of the eigenspace. That is what it's basically asking is how many eigenvectors does each eigenvalue have. And so because here we have two distinct eigenvalues in this 2x2 matrix, that means that is the maximum number of eigenvectors that we can have. So that means each eigenvalue has its own eigenvector. So that means the eigenspace for each eigenvector is 1. So for the first one, when the lambda is equal to 2, the eigenspace dimension is equal to 1. And then the same thing goes when lambda is equal to 4. The dimension is equal to 1. And so that was pretty much easy. Like I said, this is a lot less work than you think. So for the second part, part B, we are given, again, a symmetrical matrix. And what's cool about this one is that this is already a diagonal matrix. So that means our eigenvalues are 2, 2, and 3, or 2 with the multiplicity of 2 and 3. So what that means is for our eigenvalue equal to 3, the dimension of the eigenspace is equal to 1, and for lambda is equal to 2, the dimension is equal to 2 because it has a multiplicity of 2. And so for our last example, we are also given a 3x3 matrix, but this time it is not it's not a diagonal matrix, it's just a regular matrix. So as usual, find the characteristic equations and find our eigenvalues. So this will give us negative lambda 2, 2, negative lambda 2, 2, 2, negative lambda. This is equal to 0, and obviously we have no place to exploit some things for the determinant, so we're going to just use the usual with using the first row. So this would be negative lambda times lambda squared minus 4 minus 2 negative 2 lambda minus 4 plus 2 4 plus 2 lambda. And so now what I'm going to do is expand and then begin to simplify. So the first thing that I'm going to do is we can expand this first part since it's a difference of two squares. So this would be lambda minus 2 times lambda plus 2. And then we'll have plus 4. I'm going to factor out a negative 2. Be plus 4 lambda plus 2. And again, factor out a 2 on this one, so this will be plus 4 lambda plus 2. And so what we can see is that we can factor out a lambda plus 2. So this will give us lambda plus 2 multiplied by, I'm going to distribute this negative lambda. So it would be 2 lambda minus lambda squared plus the 4's, which would be 8. And this portion will just be, can be factored out into being 4 and 2. So this will be lambda minus 4 times lambda, not times, lambda, times negative lambda minus 2. And we can see that our eigenvalues is 4, negative 2, and negative 2. Or 4 and negative 2 with the multiplicity of 2. So our answer will be for the lambda is equal to 4. We'll have a dimension, or the dimension for the eigenspace will be equal to 1. And then for the lambda is equal to negative 2 case, because it is seen twice, then that means the dimension of the eigenspace will also equal to 2. And that's pretty much it for this video. This was relatively short. So this is the first example of this video, from this lecture, and we have 2 more to go before we move on to our last lecture. So thank you very much for watching, and I'll see you in the next one.